I'm Dorian Rudolph and I present the talk Quantum Space, Ground Space Traversal and How to Embed Multi-Prover Interactive Proofs into Unentanglement, which is joint work with Sevag Gharibian at Paderborn University. The central theme underlying this talk is the quantum analog of NPSPACE, which is space-bounded quantum computation. We study the complexity class QCMASPACE, where a space-bounded quantum verifier is given access to an exponentially long classical proof. Classically, this relates to Savage's theorem showing PSPACE equals NPSPACE. We use the concept of streaming proofs to avoid exponentially wide circuits for long proofs. Note, in quantum we work with the proof view of NPSPACE as opposed to the non-deterministic view. We show how to reduce streaming proofs to QMA2, and how to traverse the ground space of a Hamiltonian with local unitaries. So let's start with the introduction. Everybody knows the open problem of P versus NP. The space-bounded analog, PSPACE versus PSPACE, however, is solved. Savage's theorem proves their equality. NPSPACE can be viewed as a PSPACE machine with access to an exponentially long-streamed proof, as on the figure. The PSPACE verifier has polynomial space but exponential runtime. In NPSPACE, it gets access to a proof. The proof is streamed, so the verifier sees only one pass of the proof. Now let's look at the quantum world, where various notions of space-bounded computation have been studied. Watrous shows BQ PSPACE equals PSPACE, which is a space-bounded analog of BQP, i.e. there is no proof. Pfefferman and Remskrim show QMASPACE equals PSPACE, which is like QMA, but with a BQP space verifier receiving a polynomial-sized quantum proof. However, one might argue that the quantum analog of NPSPACE also needs an exponential length proof. This leads us to introduce the notion of QCMASPACE, which is a BQP space verifier with an exponentially long streamed proof. I'll define proof steering later more formally. Next, I'd like to present our results. First, QCMASPACE is equal to NEXP, and therefore Savage's theorem has no quantum analog. Recall, in contrast, QMASPACE is equal to PSPACE, where QMASPACE only receives a poly-sized quantum proof as opposed to QCMASPACE, which has an exponentially long streamed classical proof. The proof is a straightforward application of the PCB theorem and only requires quantum computation for randomness. Second is the universal path following lemma, which allows us to simulate any Lipschitz continuous path on the unit hypersphere within 1/x error, and using exponentially many true local quantum gates. So the unique feature of this construction is that the intermediate state, while applying the gate sequence, always stays within 1/x distance to the actual path. Hence, one can fool a quantum error correcting code with an exponentially long sequence of local errors by following a path between two code words in the ground space. Third is the embedding lemma, reducing QCMASPACE to the separable-sparse Hamiltonian problem with 1/x promise gap. Note, in this problem we only minimize energy over separable states. This allows us to reduce multi-prover interactive proofs to QMA2 with an inverse exponential promise gap in the number of bits and rounds. Next, I'll elaborate on the universal path following lemma. Suppose we have a quantum error correcting code encoded in the ground space of a local Hamiltonian with code words psi0 and psi1. A common intuition is that local errors take code words out of the ground space. This would imply that local errors cannot change psi0 to psi1 without detection. However, our universal path following lemma shows this to be false, as we can follow any path with 1/x precision with exponentially many local gates. Note that there always exists a path through the ground space between orthogonal ground states. The path following lemma allows us to approximate this path with sufficiently many true local unitaries. Note, in some intermediate states we may lie outside the ground space by 1 over exp. It is well known that there always exists a local circuit U mapping psi0 to psi1. However, the previously known decompositions use large rotations like x, y, z, or c naught that can take intermediate states far outside the ground space. For example, if we want to map from 0, 0, 0 to 1, 1, 1 inside the span of these states with two local gates and apply xxi, the intermediate state is orthogonal to the ground space. More formally, let f be a Lipschitz continuous path on the unit hypersphere. Then there exists for all epsilon greater than 0 a sequence of m exponential in epsilon and n, two local unitaries, such that all intermediate states, when applying the gate sequence to the initial state, are epsilon close to f. The idea is now to decompose f into epsilon length subsegments psi to psi plus 1. Then the rotation between psi and psi plus 1 can be written as w equals e to the ih, where h has spectral norm of at most 2 epsilon. The next lemma allows us to decompose such small rotations approximately into exponentially many two local gates, such that we can bound the sum of distances from identity of gates by epsilon to the 1 over 2n. The epsilon squared error allows us to repeat the decomposition 1 over epsilon times with small cumulative error. The maximum distance of intermediate states from psi to and psi plus 1 is bounded in terms of epsilon, albeit exponentially. We begin the proof by writing h in Pauli basis. Each term, pj, is a tensor product of one local I, x, y, or z operators. We can bound the total spectral norm in the norm of h, which is epsilon. The Suzuki decomposition allows us to then decompose U into a product of the form e to the ip, where p is a Pauli product. We can then decompose these terms into two local unitaries with the following lemma. Let h be a Pauli Hamiltonian and t a small pulse time. Then e to the ia, th can be written exactly as a product of n squared terms e to the I th with two local Paulis hj and a total pulse time of at most t to the 1 over 2n. So the pulse time of the decomposition is bounded in terms of t, albeit exponentially longer. To prove this result, we use a lemma of Clinton, Bausch, and Cubitt. Here h is 1 over 2i times the commutator of h1 and h2, where h1 and h2 anticommute and square to identity. Then u can be decomposed like this. The resulting pulse time is bounded by the square root of 2t. We apply this decomposition recursively. Let h be a Pauli Hamiltonian again. We split at qubit j, assuming pj equals z here. Then we can decompose h into h1 and h2, satisfying the conditions of the lemma. Observe that h1 and h2 only interact non-trivially at qubit j, where we use a well-known property of the Pauli operators. Note, each step roughly halves the number of non-identity Pauli terms, but it increases the pulse time from t to square root t. The recursive decomposition as a circuit then looks like this. We have h1 here and here, the h2 here and here. Next, I will briefly define the local Hamiltonian problem. We are given a k-local Hamiltonian h and n qubits. H can be written as the sum of local terms hi, each of which are Hermitians of size 2 to the k times 2 to the k, and only act on a subset of k qubits. We are also given thresholds alpha and beta with at least an inverse polynomial gap. The problem is now to decide whether the smallest eigenvalue of h is less than alpha or greater than beta. This is a promise problem, so if lambda min is between alpha and beta, the instance is invalid. We call lambda min the ground state energy and the corresponding eigenvector the ground state. The k-local Hamiltonian problem is the canonical complete problem for QMA. Here's the QMA circuit, which is like an MA circuit with a quantum verifier and quantum proof. If instead we allow a sparse Hamiltonian instead of local and optimize our separable states, the problem becomes QMA2 complete. QMA2 is like QMA, but the verifier receives two unentangled proofs. We now apply the path-following lemma to the ground state connectivity problem due to Gharibian and Sikora. This is the quantum analog of classical reconfiguration problems. We are given a k-local Hamiltonian H, states psi and phi of energy eta, and numbers m and epsilon. In the yes case, there exists a sequence of m two-local unitaries mapping psi to approximately phi, such that intermediate states have energy at most eta plus epsilon. In the no case, any sequence of length m mapping psi to phi must have energy at least eta plus 2 epsilon. They show GSCON is QCMA complete for two local gates with polynomial length and error. It is PSPACE complete for one local gate and exponential length. We show that if the sequence length is exponential and the error is sub-exponential, then GSCON has no instances for large n and is therefore trivial. This follows by using the universal path-following lemma to map from psi to phi through low-energy space. We can observe a threshold between sub-exponential error where GSCON becomes trivial and exponential error where GSCON becomes PSPACE hard. One may ask whether a large m also trivializes the one local case. We show this not to be the case, as GSCON with unbounded m and l equals 1 is still PSPACE complete. Next, I present the embedding lemma, allowing us to embed streaming proofs into an entanglement. Before that, we review the Feynman-Kitaev circuit-to-Hamiltonian construction. The idea is to reduce QMA to the k-local Hamiltonian problem by constructing a Hamiltonian H whose ground state encodes the application of the verifier's gates. This ground state is called the history state psi-hist. It has register A for the ancillas, B for the proof, and C for the time step. The history state then contains all time steps of the computation in uniform superposition. We define the Hamiltonian H whose ground state shall be the history state with an accepting proof. The input Hamiltonian H in forces the ancillas to be 0 at time step 0. The output term H out penalizes a rejecting computation at the last time step. The propagation Hamiltonian H prop ensures that the gate Vt is applied from step t-1 to step t. The first two terms of Ht model the transition, and the last makes Ht a projector. Here Vt is applied from t-1 to t, and Vt inverse is applied from t to t-1, so backwards. This Hamiltonian can easily be made 5 local and has ground state psi-hist for an accepting psi. Next, we'll define the notion of streaming proofs. One may ask, how can we stream a proof to a quantum circuit? For that, we implement the circuit here. It has 3 registers: input, ancilla, and proof. And it operates in phases. In the computation phase, it applies unitaries without touching the proof register. In the proof phase, it sets proof register with gate Wi by applying x if necessary. The proof bit is then copied to ancilla space. But how do we embed streaming proofs into the history state construction? The idea is to move the proof out of the register and into the superposition over time steps. Therefore, we define the history state with ancilla A, proof bit B, and time step C, similar to before, just that we don't have a separate proof input here. We can divide the gates into proof gates and computation gates. Proof gates correspond to the WI from the previous slide and are not known a priori and depend on the proof Y. Therefore, we write it here. So in a way, the proof is now encoded implicitly in the time steps. The challenge now is that the propagation Hamiltonian needs to know all gates in advance. But how can the history state encode the future? What if we allow two parallel worlds, or more formally, a separable Hamiltonian? Both worlds can choose whether to apply I or X at each time step. We define the FLUX gadget to enforce that both worlds apply the same gate. It consists of HTI times HTX plus HTX times HTI, which is the transition Hamiltonian for gate X or I respectively. Therefore, we don't fix the gate a priori, but this gadget simulates the Boolean equality function because if, for example, the first world applies an X and the second an I, then the first term would be violated. The low energy state is now supposed to be the tensor product of two history states for an optimal proof Y star. But this is unsound, as states of this form here are in the ground space, as both HTX and HTI are annihilated by the plus state since it is invariant under both X and I. The fix is to use IX instead of X, which is a non-trivial insight. We can now define the complete Hamiltonian from the FLUX gadget. Again, we have H-in, H-prop, and H-out. But now there are left and right terms. In H-prop, the FLUX gadget is only applied to proof gates. But this is still unsound with FLUX gadgets on multiple time steps. Suppose the left term has only weight on the last time step and the right only on the first time step. Then L annihilates all time steps but M and R all but 0. The fix is to enforce symmetry by using the projector onto the symmetric subspace. Then, if Hsim times psi L tensor psi R is 0, psi L and psi R must be equal. Further note that Hsim is not local but only sparse. Now let's analyze parts of the FLUX gadget. Unfortunately, we don't have time to go in depth here. So if we set the left register to psi 1, then we can show that any low energy state on R must implement the unitary U parameterized in AT and BT, which is the normalization of the term AT times IX plus BT times I. We can diagonalize the residual propagation term on the R system, which is obtained by applying psi 1 to the left Hamiltonians. Here we have the residual propagation term again, and as in Kitaev's proof, we conjugate by the unitary W. And we obtain a tri-diagonal matrix. Note that we get AI and equals 0 and BI equals 1 or vice versa if the prover is honest. Then W has -1 on the off diagonal and 2 on the diagonal, just like in Kitaev's proof. Finally, we state the embedding lemma. Consider a quantum verifier Q with m local gates and classical streaming proof of length 2 to the p, q ancillas, and a threshold gap of 2 to the minus r. Then we can reduce Q to a separable sparse Hamiltonian instance H on O of Q plus log m qubits with a gap of omega of 1 over 2 to the r times m. As a corollary, we can reduce QCMASPACE with proof length p and q ancillas to the separable sparse Hamiltonian problem with a gap exponential in the proof length. We can also reduce MIP with p provers r rounds, u space, and t bits of communication per round to SSH on O of u qubits with a promise gap of omega to the 2 to the minus tr times p. The proof uses the standard trick of sending the concatenation of all interactions between prover and verifier as proof to a QCMASPACE verifier. Lastly, we show that a particular version of GSCON is next complete, namely with a sparse Hamiltonian 1 over x promise gap, exp many 2 local gates that are required to not interact across a given bipartition of the qubits, with the consequence that intermediate states are separable. We conclude the talk with open problems. GSCON with exponential length and 1 over x exp gap lies somewhere between PSPACE and NEXP. Can we improve these bounds? Can the embedding lemma be extended to allow for more gate choices? So not only I and x. Currently our proof requires the structure resulting from using I and IX. The embedding lemma recovers the result of Bleer and Tapp that NP has a log size QMA2 proof with 1 over polygap. Can this be improved to a constant gap? Thank you for listening. Feel free to send me any questions you may have.